Okay, we started with this molecule here, and it says practice the act of recognizing the patterns of resonance and using curved arrows to push electrons and show their delocalization. We already identified two of the patterns. We have an allylic lone pair is one of them. Another one is that we have a lone pair next to a carbocation. Is there anything else in here that anybody recognized from one of the patterns that we looked at, one of the 5 patterns? It's definitely not anything to do with conjugation, because there's no aromatic ring in here, and there's no pi sigma bonds alternating. There's one more pattern in here. Anybody recognize the other pattern? What if I told you it was right here? It's right here. If we go back, okay, we said that when you have a pi bond between atoms of differing electronegativity, the pi electrons are going to be attracted to the more electronegative element. So we could label that one too. We have pi bond, I'll put here between nitrogen and carbon, and they have differing electronegativities. Okay, so we've recognized 3 patterns here. I'm going to erase all this because now we're going to try drawing some curved arrows. So we'll erase all of this, and let's give it a shot. Okay, I'm going to start with the allylic lone pair, which is here. Remember that we have a double bond, and then this is an allylic position, this is an allylic position, this is an allylic position, but this allylic position has a lone pair on it. It has 3 of them, as a matter of fact, and so we can draw a resonance contributor for an allylic lone pair. Let's start by drawing our closed bracket. This, we're going to put our resonance arrow, and we're going to draw the pattern for an allylic lone pair. We're going to make a pi bond between the carbon and the oxygen. Then we're going to break this pi bond, and we're going to put the electrons on this carbon right here. And so let's draw what we end up with. And this is a 7-membered ring. Mr. Dion is not God's gift to drawing 7-membered rings. But anyhow, so it looks something like this. So now we've got this over here. We've got our double bond here. We have our pair of electrons here. And we still have a pair of electrons here and a positive charge right here. Well, there we go. So let's see. That's our first resonance contributor. Give me a thumbs up if you follow me on that contributor. All right, good. The allylic lone pair, cool. Okay, well, something I noticed right away, right here, is that I have a pair of electrons on that carbanion right next to the positive charge of the carbocation. So I'm going to put those electrons in here to fill up that empty p orbital. So I'm just going to dump them in here, make a pi bond. Yep, that's what I'm going to do. So I'm going to draw that resonance contributor. See here, like this. So, you know what I'm going to do? I'm just going to copy and paste it. That would be easier since I'm using an iPad. So I'll just copy this guy and then paste it over here. There we go. All right, so now that we've done that, that is going to fill that up like this. Am I missing a double bond? I am missing a double bond. Oops, I made a mistake. See, this is why it's like riding a bike. So I left out a double bond. I thought there was something fishy about this. There we go. No, I didn't leave out a double bond. Where am I? There we go. Okay, so I was good here. There we go. And then I had my carbocation here, so I made a double bond like this. Good. All right. So there we go. So fill those in, and then I have another resonance contributor that I could draw. So if I look at the pi bond that's between two atoms of differing electronegativity. Nitrogen is more electronegative than carbon, and thus I can break that pi bond and put the electrons on the nitrogen. Excuse me. And I'll just paste this guy again. So what that's going to give me, I'll move this resonance arrow so it's a little bit prettier. So it will look like this. So I'll fix all this, end up with this, and then I broke that pi bond, this one here, and now I end up with a negative charge on my nitrogen and a positive charge on my carbon, like that. So that would be another resonance contributor. And I'd say that there's one other one that I haven't put in, and I'll use a different color curved arrow for this one. If you were to take this, you might have realized or recognized that since you have a lone pair next to a carbocation, you could also draw another resonance contributor where you take a pair of electrons and you make a pi bond here so that the carbon gets an octet. And so what that would give you would look like, let me just paste this thing again. So that's going to give you something that looks, where's my structure? Here it is. So what that would look like, let me fix this up here. So this is just the result of the blue arrow only, the blue curved arrow only. What you would get would be something that looks like this, where you have a double bond between the carbon and the nitrogen, and now the positive charge is on the nitrogen, and we have our double bond here still like that. So this would be another resonance contributor, but those are all perfectly legitimate resonance contributors. Now, I don't think this is a simple problem, and so I would expect that maybe you got some of these, but maybe not all of them. And so let's try a practice problem. Over to a blank document here, and we'll try a practice problem and see if we can work our way through one. Like, let's try something like this. Let's say we have a 6-membered ring. We got 2 double bonds. We have an oxygen with a negative charge, and we have a double bond over here. And what we want to do is we want to draw resonance structures for this ion. Okay. Well, the first thing I'll ask you is, does anybody recognize any of the patterns in this ion? Any of the patterns, the 5 patterns that we looked at? There's no allylic carbocation because there's no positive charge. There's no aromatic ring. We have conjugation, yes. We have an allylic lone pair. That's where we would want to start. Yes, absolutely. An allylic lone pair. So you could put here allylic lone pair. And yes, the fact that it's conjugated, right? Because you have double, single, double, single, double, single, double, right? There is conjugation, and so we can use that to draw resonance structures, but we're going to have to start with the allylic lone pair. Okay, so what are we going to do? The same old 2 curved arrow pattern that we've always drawn. We take one of the pair of electrons, we make a pi bond. That would give this carbon 5 bonds, which is impossible. So we're going to have to break this pi bond and put the pair of electrons on this carbon. Well, let's draw what we would get from that. So what we end up with is the 6-membered ring. We didn't touch this bond. We didn't touch this bond. Now we have a double bond between the carbon and the oxygen. We have the 2 lone pairs left on the oxygen, and we have the lone pair over here. What happened to the negative charge? We had a negative charge here. We must have a negative charge somewhere here. Could anybody tell me where the negative charge is now? Yes, exactly. It's on the lone pair that's on the carbon. Absolutely. So now we have a carbanion here. And we can keep going, can't we? Because now we have another allylic lone pair. right here. What I have highlighted in yellow is another allylic lone pair. And so we can take the pair of electrons here. Oops, need my red pen. We can make a new pi bond. We're going to break this pi bond, and we're going to put the electrons on this carbon. And let's draw that resonance contributor. Draw the 6-membered ring. I didn't touch this bond. I didn't touch this bond. I've made a new pi bond here, and now I have the pair of electrons here. And so my negative charge is over here on this carbon. There's one more resonance structure I can draw, isn't there? Because we have another allylic lone pair now, which is right here. Right? We're just looking for allylic lone pairs. So I'm going to take that lone pair. I'm going to make a new pi bond. I'm going to break this pi bond, and I'm going to put the pair of electrons on the carbon that's outside of the ring. And so I end up with something that looks like this. There we go. Like that. And just like that, we're done. We've drawn all of the resonance contributors for this compound just by looking for allylic lone pairs. Give me a thumbs up if you follow me on that one. And if you have any questions, don't hesitate to stop me. Okay. Let's try another one. What if I give you something like this? And this time I'm going to give you a minute to give it a shot on your own. So without me doing it with you right away, because again, it's like riding a bike. You can watch me do it, but you need to be having a piece of paper and a pencil and practicing it yourself. Okay, you can see that you've got an allylic lone pair right here. So I want you to take a second and see if you can start drawing some resonance contributors. I'll give you 90 seconds to start. Hey Siri, set a timer for 90 seconds.
1 minute and 30 seconds. Counting down.
Excuse me. Okay, thanks, Siri. All right. So, could anybody tell me how many total resonance structures they were able to draw? Besides this one, how many more could you make? So you have this one plus how many? Anybody? If you're not sure, we could start by drawing some and see where it takes us. All right. So we have an allylic lone pair. What are we going to do? We're going to take the pair of electrons from the carbanion. We're going to make a new pi bond like this, and then we're going to break the pi bond, and we're going to put the pair of electrons on this carbon. That's part of the allylic system. Okay, and then we draw a resonance arrow, which is a double-headed arrow, like this. I'm going to redraw the 6-membered ring. I like to start by drawing the things that are unaffected. So this double bond and this double bond didn't do anything. Now we're going to have a new double bond right here, and we have a pair of electrons here. So we put our negative charge here. There's our carbanion. And you can see that now we have a new allylic lone pair. You can use the same two curved arrows. We make a new pi bond, and we're going to take the pi electrons and we're going to put them on this carbon. And we can draw the new resonance contributor, which is going to look like this. We're going to have the pair of electrons over here. We have a new pi bond here, and we have this pi bond here. All right. And then we can draw another resonance contributor because we have another allylic lone pair. And let's draw that out. So I'm going to take the lone pair, put it here, break the pi bond, put the electrons on the end. I end up with something that looks like this. Or I have my negative charge over here, pi bond here, pi bond here, and I didn't touch this pi bond on the end. And that is our last resonance contributor. Did anybody get all those resonance contributors? Okay, cool. Great. If you're wondering, and again, I would never ask you to draw this on a quiz, but if you're wondering, what would the resonance hybrid look like here? Well, if you draw the carbon skeleton, meaning the parts, all the different carbons, okay, it would look something like this. And you would kind of say, well, all of the pi electrons, all three of these and the lone pair, so those 8 electrons are shared between all of these carbons. You would kind of put a dash around all of these like this. And then the negative charge was here in the first structure, then it was here in the second one, here in the third, and here in the last. And so all 4 of those carbons have a partial negative charge. How do you know when to stop? You know when to stop when you've run out of possibilities. You look at this structure and you say, well, there's no more allylic lone pairs, so there's no other resonance contributors that we can draw. It's just part of looking at the molecule and knowing the rules. And you say, well, there's no rules that I can apply, so there's no more resonance contributors that I can draw. I'm done. Would anybody like to try one more? Anybody want to try another one? Okay, let's try one more, and then we'll move on and we'll finish up chapter 2. So let's try one more. Try something that looks like this. So what if we have carbocation, then put a double bond here, a double bond here, and then there we go. So what if we have something that looks like this? Could anybody tell me where you would start here? Where would you start? What's the first pattern that you see here? The only thing that we have of those 5 patterns. We do have conjugation, but there's something that we saw even before the conjugation. We do have an allylic lone pair technically. Yes, we do have an allylic lone pair here. Okay, you could start with that. Is there anything else that's allylic that you see here? Yeah, we have an allylic carbocation, don't we? Right, we have an allylic carbocation here. So I would always start with the part that's got a charge first. And so we could start by pushing an arrow like this, right? This is an allylic. This system is allylic, pi bond, and then a sigma bond. This is an allylic carbocation. And so we push one arrow to take these pi electrons and to put them so that we fill up the empty p orbital on the carbon that has the positive charge. So I want you to take a second and see if you can draw what the result is of drawing that curved arrow. And could anybody tell me where the new, where the positive charge would be now? Yeah, it's on the carbon. That's part of the allylic system, isn't it? Right? So if we draw something that looks like this, now we've put the pi bond over here. We have a pi bond here. Okay, and now the positive charge has moved. Okay, it's showing the delocalization of that positive charge. So now we have another allylic carbocation right here. So let's push that arrow. We're going to fill up that empty p orbital, and we're going to end up with something that looks like this. We're going to end up with something that looks like this, and this, and this. So now we have the positive charge here. And the last one is that we have a lone pair next to a carbocation, like that. And so we're going to push those arrows to show the delocalization of the electrons from the oxygen in here. And now I end up with this, and I'm going to draw the bond to the hydrogen. So I end up with this, like that. And now I've got 3 bonds to oxygen in one lone pair. So my positive charge is on the oxygen. Oops, got my close bracket on the wrong side. And there you go. Those are all of the resonance contributors. We're not necessarily trying to move the charge to the lone pairs. What we're trying to do is recognize any of the 5 patterns that we saw. So you go back to the 5 patterns. Oops, that's not it. There we go. So we go back to the 5 patterns that we looked at, which start somewhere around here, okay? And we start looking for these, okay? We look for an allylic lone pair, an allylic carbocation, lone pair of electrons, etc., etc. And we're just trying to show the delocalization of the electrons. But the only way that we can show the delocalization of the electrons is if we follow these rules, these 5 rules. They always have to be obeyed in order for us to, or these 5 patterns, I should say. We have to look for these 5 patterns in order to draw resonance structures. All right, well, let's move on from there. And let's move into section 2.11. So let's go all the way through this. We've already covered all this. And once you draw all of these resonance structures, another thing you've got to be able to do is assess the resonance structures. So you've got to be able to look at all the resonance structures that you've drawn, and you've got to assess, okay, well, let's say I've got 4 resonance structures, or I've got 2 resonance structures. Is one of them going to be more significant than another? Put another way, is one of them going to contribute more to the resonance hybrid than another one? And the answer is yes, one of them is going to contribute more than the other oftentimes. Not always, but oftentimes. How do you determine whether one is more, is a greater contributor than another? Well, you follow these rules. The first rule is this. The most significant resonance form is going to be the one that has the greatest number of filled octets. I actually showed you this rule this morning before we learned it. But if you look at these 2 resonance structures here, there's nothing wrong with either of them. However, the one on the right is the major contributor because in it, the carbon has a complete octet. Okay, the oxygen also has a complete octet. And if you're saying, well, how does it have an octet? It's got a charge. Just because something has a charge doesn't mean it doesn't have an octet. The oxygen here is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. It does have an octet. And the carbon is surrounded by 1, 2, 3, 4, 5, 6, 7, 8 electrons. So it has an octet. If I go over to this structure, you can see that the oxygen is surrounded by an octet, but the carbon is only surrounded by 1, 2, 3, 4, 5, 6. Even though this is a valid resonance contributor, it is going to be the minor contributor, and this would be the major contributor because every atom has a complete octet, except for the hydrogens, of course, which can't have octets. So that's the first rule. The second rule is we always try to avoid having multiple formal charges. You don't want to have a pile of formal charges in your resonance structure. If you look at these 3 resonance structures here, there's nothing wrong with any of them. They're all perfectly legitimate. All of them are totally reasonable. However, in this one, we have no formal charges. No formal charges. Whereas in the other ones, we have 2 formal charges. And so the one that has the least number of formal charges is going to be the greater contributor of all 3 of these. And so we put that this would be the largest contributor, and these 2 would be minor contributors. I know that this one says major contributor, but there's a reason why this would be the greatest contributor, so we'll put that in first place. This would be third place, and this would be second place. And I'll explain why this would be a greater contributor than this one in just a second. The next rule answers that question, is that if you have a structure that's got a negative charge in it, the negative structure is always going to be, the greater contributor is going to have the negative charge on the more electronegative element. If you take a look at these 2 resonance contributors, there's nothing wrong with either of them. In both of these that we're looking at right here, in both of these, every atom has a complete octet. However, in this one, the negative charge is on an oxygen. In this one, it's on a carbon. Since oxygen is more electronegative than carbon, this will be the major contributor. If you look down here at the resonance structures of an amide, we have a positive charge, son of a gun. Jumping around here. Here we have a positive charge on an oxygen, and here we have a positive charge on a nitrogen. Well, oxygen is more electronegative, and so it's going to be less comfortable with a positive charge than a nitrogen will. So this will be our major contributor. If we go back to the example we just looked at, the reason why, if you compare these 2, that this one is going to be, the reason why this one would be the minor contributor is because the carbon doesn't have a complete octet. However, this nitrogen does have a complete octet. Somebody asked, when you are saying significant, is this resonance also the most stable? Not necessarily. No, it doesn't mean it's the most stable, because remember that these are not individual structures. This is a main take-home message about resonance. It's not in this form 1 minute, in this form the next second. It's got nothing to do with that. It's like going back to the nectarine analogy. A nectarine is not a plum 1 minute and a peach the next minute. It's just a nectarine. The actual resonance structure, it's very difficult to draw a single resonance structure that represents resonance for an entire molecule or ion. And so we use the best model we have. And so we draw resonance structures, several of them, that show how the electrons and charges are delocalized across the entire resonance hybrid. Okay, these are both part of the same thing. All right, it's not that one is more stable than the other, but if you were to look at an electrostatic potential map, let's say, and if you were to go and look at this one here, for example, you'd have more negative electron density in this part of the molecule than you would in this part of the molecule, because the negative charge is more comfortable on a more electronegative atom. Does that help? It means, yeah, it means it's the greater contributor. All right, and rule number 4, if the compound has an overall formal charge, focus only on drawing resonance forms that show the delocalization of the charge. So here we have a negative charge. Here we have a negative charge on the oxygen, so we just want to focus on showing the delocalization of that charge. We don't want to start trying to make new charges just for the hell of it. Okay, let me give an example. If you were to take this compound, and I'll redraw it here with my black pen. If you took this resonance contributor, this right here, like that, and if you were to say, well, I've got a pi bond here, couldn't I draw something like this and then end up with this, where you would have a negative charge still here, then you'd have a CH2 like this. So then you'd have a negative and a positive here. Now you're just making more and more formal charges. Okay, you started it with 1, and now you've got 3. You always want to avoid doing that. So that is this resonance structure right here. You want to avoid doing that. And that's why if we go back to that practice problem that we were looking at a few minutes ago, this one down here, when we started out with this molecule, so we started it with this cation. So let me just copy it and paste it down here. Okay. So I saw that somebody or was looking in the chat, and somebody said, well, why can't we just start, moving the electrons here? Because I have an allylic lone pair, why can't I just move these around like this? The reason why you can't do that is because if you did do that, you would end up with this, where you have the double bond here, and then you have a pair of electrons here, and then you have a double bond here, and you have a positive charge here. And so the reason why you wouldn't do this is because now you're just creating new formal charges. And you don't want to just create new formal charges at random. We want to show the delocalization of the existing formal charge. So let's go back to our slides. Somewhere around here. Oh, no, we were past that. Okay, so you want to avoid making charges just for the hell of it, so to speak. Okay, with all that in mind, it says draw the significant resonance forms of each compound and indicate the major resonance form. Well, let's take a look at this first one here. This is called Amide. You don't need to know that. I'm just sharing the name just so you get the feel of organic names of organic molecules and ions. Since the nitrogen has a negative charge, we know it has 2 bonds and 2 lone pairs. So where are we going to start? We want to show the delocalization of that negative charge. Do we have an allylic lone pair? The answer is yes, allylic lone pair right here. So let's start by drawing some curved arrows. We're going to put a pair of electrons between the nitrogen and the carbon, and we're going to move a pair of electrons over here onto this carbon in the ring. That's going to give us something that looks like this. So we have a pair of electrons here, pi bond, excuse me. There we go. So what I'd like you to do is take the next minute and try to draw 2 more resonance contributors for this ion. So I'm going to give you a minute to give that a shot. Hey Siri, set a timer for 60 seconds.
1 minute, starting now.
All right, time's up. So could anybody describe how they made the next resonance contributor? And you could unmute your mic or type it in the chat. How would you draw another resonance structure here?
What I did for the next one was I took the lone pair of electrons and moved them downwards to make a double bond, and then took the double bond and then put that into a lone pair of electrons on the carbon that's like pointing downward the most. I don't know how to explain that.
That's perfect. That's better than I could have done. Who is that?
I'm Tracy.
Hey, Tracy, that's better than I could have done. I couldn't explain it any better than that. I know exactly what you meant. Right, so what Tracy says is, take this pair of electrons. We're going to make a new pi bond here. We have an allylic lone pair, same old pattern. We're going to break this pattern, and she says we're going to put them right here on this bottom carbon. That's best explanation. I see Andrew posted something in the chat. Hold on, Andrew. I'm going to... Beauty. Perfect. I see Andrew drew the exact same thing. Okay. Let me just point out something, and this is a real nuance, and you'd have to, and every once in a while I'll run into students who are real sticklers and they're wondering about every little thing. Look, sometimes I'll have people that'll say, well, Mr. Dion, could you draw the curved arrow inside of the ring like this and like this? Could you do? The answer is yes. Okay, you're just showing the delocalization of the electrons. Technically, you could do this if you really, well, don't do that because that's ugly, and I would, I wouldn't give that a passing grade on a quiz. But the idea is you're just showing the movement of the electrons, okay? So you can do it inside the ring, outside the ring, as long as the tail starts on the pair of the electrons and the tip ends up between these two carbons. Mr. Dion is a happy camper. All right. And then here we have this pair of electrons coming down here. So perfect. Thanks, Tracy and Andrew. You're both 100% correct. And so let's draw that resonance contributor like that. When you're teaching over Microsoft Teams, we improvise, adapt, and we try to overcome anyway. All right. So we have a negative charge down here. And is there another resonance contributor that I could draw here? We have 3 so far. Is there another one? There is another one, right? Because we have an allylic lone pair here. We have a lone pair and a double bond here. So we can draw one like this, where we take this pair of electrons, make a new pi bond, and we move this pair of electrons up here. And there we go. We've got another resonance contributor. Here we go, like this, and like that. And there you have it. Those are all of the resonance contributors. And if you're sitting there going, well, hold on, Mr. Dion, I drew another one. I took this pair of electrons and I put them up here and I drew this. Okay, and technically there's nothing wrong with this at all. But you would just end up where you started off. So if you drew that one, good, no problem, but not necessary because this and this are identical. So not really required to do that. Okay, so I'm going to erase that. I'm going to label these resonance contributors as A, B, C, and D. Could anybody tell me which one of these contributes the most to the overall resonance hybrid? Would it be A, B, C, or D based on the rules that we learned? We've got a negative charge. What if, okay, all right. No, they all have a negative charge, but if we go back here, what was the rule here? Rule number 3, a structure with a negative charge on the more electronegative atom is going to be the most significant. So we've got everything in here has an octet. There's nothing in here that doesn't have an octet. Every atom in here, except for the hydrogens, has an octet. Yes. Thanks, Kiana. It's A. Perfect. All right, why? Because in that one, the negative charge is on the most electronegative element. So we'll put here, let me use my red pen. We'll put A, son of a gun. Who's in it here? Sorry, every time I and I'm left-handed, so every time my left hand touches the thing on the side, it moves the screen around. So we'll put A is most significant because negative charge is on most electronegative atom. There you go. Nothing to it. Let's try one more. We'll see if we can evaluate what's the most significant resonance contributor. This one. So we'll start by putting a closed bracket, or open bracket rather, here. Let's draw in the lone pair that's missing. So we're missing a lone pair right here. And what are we going to do? Well, the first thing I notice is you have a lone pair next to a carbocation. Let's take that pair of electrons and let's share them between the nitrogen and the carbon so that we can get rid of that positive charge on the carbon. So we end up with something that looks like this. We have this, and we have a double bond here. I have a friend who was really annoyed whenever somebody drew a double bond outside of a ring. And you always got to draw it inside the ring. It doesn't matter, but we'll put it like that. Where's my positive charge now? I had a positive charge to start with. That means I'm still going to have one somewhere. Could anybody tell me where the positive charge is in this contributor? Yeah, absolutely. It's on the nitrogen. Because when we know that when nitrogen has 4 bonds, it has a positive charge. So we'll throw that in there. And, oh, there's another resonance contributor that I could draw here, can't I? And I could have drawn it a little bit differently than I have here. But there's one more where if I do 2 arrows at once, if I put these electrons back here and then I make a double bond here, it's kind of a double whammy here, then I end up with a resonance contributor that looks like this. So like this, and then I have the double bond here, and I have the positive charge over here. Out of all 3 of those, could anybody tell me which one of these would be the major contributor? I'm going to call this one A, I'll call this one B, and I'll call this one C. Yeah, it's going to be B. Why would that be, Andrew? Or anybody? This one is going to be the most significant, yes? No, that you couldn't use that rule because nitrogen is more electronegative than carbon. So nitrogen is actually less comfortable with a positive charge. Nitrogen is more comfortable with a negative charge. Let's go back in the rules here. Rule number 1 was the most significant resonance form has the most number of filled octets. Kiana's got it. Yeah, absolutely. We go back here. We say all octets filled. There we go. All the octets are filled here. And so there you have it. This would be the greatest contributor to the resonance hybrid.